In this section, we will give the final version of the graph sketching technique. So when we summarize the graphing strategy in the section 2 of chapter 4, we omit one important topic: asymptotes. Polynomial functions don't have any asymptotes. Asymptotes of rational function were discussed in the section 2 of chapter 2. But what about all the other functions, such as logarithmic and exponential functions? Since investigating asymptotes always involves limit, we can now use the L'Hopital rule, which is given in the previous section, as a tool for finding asymptotes of many different types of the functions. So our strategy to sketch the graph can be given as the follows. Okay, let's analyze this procedure. First of all, you should analyze the function f of x. How you can analyze the function f of x? By considering the domain. Okay, so you should calculate the domain of the f, and you should find the intercept. How we can find the intercept? We have two intercepts: x-intercept and y-intercept. Y-intercept is 1, but x-intercept can be more than 1. So for the x-intercept, how we can find the x-intercept? By solving the equation f of x equals y. F of x equals 0, y equals 0 case. So from here you can find the x-intercept. For the y-intercept, you can find the y-intercept as a result of the zero value of the function. Y equals f of 0 is the y-intercept. Okay, actually we discussed all of them in the previous sections. And you should find the asymptotes. So for the asymptote, let's recall. In this section also I will give the oblique asymptote. But first of all, let's discuss the vertical asymptote and the horizontal asymptote. Vertical asymptote and the horizontal asymptote. Vertical asymptote is vertical asymptote or asymptotes can be calculated easily by considering these limits. Limit of f of x when x goes to infinity, and limit x when x goes to minus infinity, f of x again. So if one of this limit goes to some constant number, let's say L1 and L2, so this implies y equals L1 is a not vertical, sorry, it's a horizontal asymptote. This is the horizontal asymptote. Okay, is a horizontal asymptote because this is give us the information about the behavior of the graph of the function from the rightmost side and leftmost side. Okay, so second one says y equals L2 is a horizontal asymptote. Actually, in the graph you can observe, if this is the function value, this is y equals L function, graph of the y equals L or y equals A. Okay, so this is a horizontal line. For the vertical asymptote, you should find the some point where when x approached at that point, when x approached to that point, limit goes to infinity or minus infinity. So limit when x goes to a from left or right, one of them is enough. Also here one of them is enough. F of x equals plus or minus infinity. Plus infinity or minus infinity. In this case, x equal a is a vertical asymptote. or from right hand side it goes to plus infinity or minus infinity. X equal A is a vertical asymptote. For any case, I strictly recommend to discuss the limit from left side or the right side of your point, because when sketching the graph, you will need the both limit value. And also we have oblique asymptote. If there is no horizontal asymptote, we can talk about the oblique asymptote, but in the following parts you will learn. In the second step, you should analyze the f prime. How you can analyze f prime? By finding the partition number of f prime and the critical number of f. As you know, these are different. All critical number are partition number, but partition number can be more than the critical numbers. So construct a sign chart for f prime by using the partition number for f prime. Okay, then determine the interval on which f is increasing and decreasing, and finding the local maximum and local minimum of f. You can analyze the f prime. In the third step, we analyze the second derivative of the f by the similar way. Sometimes I will calculate the first derivative and second derivative, and by making the sign chart of the f prime and f double prime together, I will discuss the interval where f is increasing, decreasing, concave up, concave down, and I will find the point where f has a local maximum, local minimum, and inflection point, etc. And by using all this information, you can sketch the graph of the f, because in each interval you know the behavior of the function, and you know the intercept, you know the asymptotes, and by using all of this information you can sketch the graph. Okay, as application of this procedure, let's sketch the graph of the one function. Actually, from the past year exam question, I will solve. F of x is x squared plus 1 over x plus 1. So I will sketch the graph of this function. Okay, the question is graph. Graph function f of x. Okay, this is our question. So step 1, you should analyze f. So what is the domain? For the domain of the f is all real number except point which makes denominator 0. Okay, so if x plus 1 equals 0, this implies x equals minus 1. The function is indefinite. The function is indefinite. So 1 is not in the domain, so we should subtract the 1 from the real numbers. And this is the part A of the step 1. Okay, from here you can see. In the part B, we should calculate the intercept. So x-intercept and y-intercept. X-intercept or intercepts and y-intercept. How we find the x-intercept? F of x equals 0. By solving this equation you can find. So x squared plus 1 over x plus 1 equals 0. So it is possible when x squared plus 1 equals 0, but there is no solution. Okay, no solution. What does it mean? No x-intercept. For the y-intercept, y equals f of 0 is the y-intercept, so which implies 0 squared plus 1 over 0 plus 1, which is 1. So y equals 1 is the y-intercept. So what does it mean? In the graph, y equals 1, our curve have to pass through to this point. Okay, I don't know what is the curve, but it have to pass through to this point. And there is no x-intercept, so it is not possible here like that one. And part C, of the step 1 is the asymptotes. So you should look the following limit, okay, for the asymptote. We have two asymptotes, vertical, okay, first horizontal asymptote, this is to check the horizontal asymptote, second one is the vertical asymptote. For the horizontal asymptote, you should check this limit x goes infinity f of x. So limit x goes infinity x squared plus 1 over x plus 1. Here we have a infinity over infinity interminant form, or from the first section you know this is infinity, but by applying L'Hopital rule we can show that when x goes to infinity 2x over 1, so this is 2x goes to infinity, so this is infinity. Okay, so there is no horizontal asymptote from the first limit, and also from the second limit there is no horizontal asymptote for the minus infinity when x goes to minus infinity. Okay, you can show that easily when x goes to minus infinity. This goes to minus infinity by the above idea. By using L'Hopital rule, you can show that. For the vertical asymptote, the point which is not in the domain is the candidate to be go to infinity. Actually, if a point makes denominator 0 for the quotient function, this means it can be infinity or minus infinity when x approach this value. So you should look to this limit x goes minus 1 from left side, and limit x goes minus 1 from right hand side, f of x function x squared plus 1 over x plus 1. Here numerator goes to 2, denominator goes to 0, but when x is less than minus 1, here x is less than minus 1, so x plus 1 less than 0, so it's approach 0 from left side, so 2 over 0 goes to minus infinity. When x goes to minus 1 from right hand side, x squared plus 1 over x plus 1, again let's use the green color, this goes to 2, this goes to 0. Here x minus 1, x bigger than minus 1, x bigger than minus 1, so x plus 1 bigger than 0, so it approaches 0 from right hand side, so this limit is plus infinity. Actually, geometric interpretation of this result is, first of all let's write our conclusion. So this 2 implies x equals minus 1 is a vertical asymptote. Okay, so geometrical interpretation of this result is x equals minus 1 is a vertical asymptote. So this is x equals minus 1 line. So from left side, function goes to minus infinity. So graph goes to minus infinity from left side. When x approach minus 2 from left side, function goes to minus infinity. From right side, function goes to plus infinity. So the behavior at the point minus 1, like this one, it goes to plus infinity from right hand side of the minus 2. So by this way we complete the step 1. In this step 2, we should analyze the first derivative. So you should calculate the first derivative of the f of x is x squared plus 1 over x. So you should evaluate the derivative of the f of x. Okay, I will make the sign chart together. Derivative of the f of x is derivative of numerator 2x times denominator minus derivative of denominator is 1 times numerator x squared plus 1 over x plus 1 square. So this implies 2x squared minus x squared plus 2x minus 1. This is x plus 1 square. Okay, so this is our f prime. So what is the partition point or critical point is enough actually. Okay, if you focused on the critical point, that's enough. So f prime of x equals 0 and f prime of x is undefined. So this implies when x equals minus 1, it's undefined. So for x equals minus 1, f prime is undefined. Okay, but x equals minus 1 is not in the domain of the f. So this is not a critical point, but partition point. Okay, so this implies f equals minus 1 is a partition point. Partition point. Okay, but not a critical point. Let's emphasize, not a critical point. So at that point, there is no local minimum, local maximum, etc. That means, okay. So f prime equals 0 implies x squared plus 2x plus 1 over x plus 1 squared equals 0. This implies numerator equals 0. So this is not plus 1 minus 1. What is the delta of this quadratic function? B squared for 2 squared minus 4 times b times c. This is 8, okay? So we can find the roots of the this second degree polynomial. So x1 and x2 equals minus b plus minus square root of delta over 2a. So this is 2 square root of 2. So minus 1 plus minus square root of 2. Okay. So we have a 2 critical points. These are different than the minus 1. So these are the critical points. Okay. So are critical points. I will make the sign chart later. Okay. So let's look at step 3. We should calculate the second derivative of the f. So f double prime is from the here we should calculate. So derivative of x squared plus 2x is 2x plus 2 times denominator x plus 1 square minus derivative of the denominator 2 times x plus 1 times numerator x squared plus 2x minus 1 over denominator square of square is power 4. So let's make some arrangements here. Actually this is x squared plus 2x plus 1. So 2x cubed plus 4x squared plus 2x plus 2x squared plus 4x plus 1. Just I distribute to that part, but space is not enough. Okay, let's write here 2x cubed plus 4x squared plus 2x plus 2x squared plus 4x plus 1 minus 2x times x squared 2x to power 3 minus 2x minus 4x squared minus plus 2x, and we multiply minus 2x squared minus 4x minus plus 2 over x plus 1 to power 4. Okay, let's write our functions. These are cancelled, so there is no x to power 3 term. 4x squared are cancelled, 2x squared are cancelled, 2x, 6x, these 4x are cancelled, so we have 4x. Yes, so this is 4x plus 1 plus 2 plus 3 over x plus 1 to power 4. So what is the partition points of the or partition number? Okay, partition number of the f prime. So this is critical number. So f double prime equals 0 implies 4x plus 3 over x plus 1 to power 4 equals 0. So 4x plus 3 equals 0, x equals minus 3 over 4. And f double prime is undefinite implies x equals minus 1. Okay, so these are the critical partition number of f double prime. So let's make the sign chart according to the these values. This is x, f prime, f double prime, and behavior of the f. What is our points? Let's look. For the f prime, minus 1 minus square root of 2, minus 1 plus square root of 2, minus 1 plus square root of 2 is bigger than the 0. This is positive. Minus 1, actually at the point minus 1, the function is indefinite, and minus 3 over 4. Which one is minus 3 over 4 is bigger, or minus 1 minus square root of 2 is bigger? Okay, we should decide. So minus 1 minus 3 over 4 and minus 1 minus square root of 2. So this is less than minus 1. Okay, so it is easy. Minus 1 minus square root of 2 is the zeros of the f double prime. No, f prime. Yes, this is 0 here, sorry. And minus 1 at the point minus 1, f double prime indefinite and f prime indefinite. Both of them are definite, and also f is indefinite. And at the point third, what is the other critical point? It's minus 3 over 4 and minus 1 plus square root of 3. Minus 3 over 4. Here f double prime 0 and 1 plus minus 1 plus minus 1 plus square root of 2. Okay, this is the root of the f prime. So let's make the sign chart. For x equals 0, f prime, for x equals 0, f prime is negative. Minus 1 over x plus 1 square minus 1. Okay, where is the 0? 0 is here. So this is negative. Negative f prime. So here also negative. At the point minus 1, it can change the sign. So let's look to some value for x is less than minus 1 but bigger than minus 1 plus square root of 2. But denominator is always positive. So when x is less than minus 1 minus square root of 2, this is negative. So it is negative again, because double root denominator. So here this is positive, here this is positive. Okay. And for f double prime, when making the sign chart, please be careful. If you make a mistake, you cannot sketch the graph. When sketching the graph, you can sense the wrong part actually. So for x equals, what is the sign of the f double prime? For x equals 0, this is 3. So positive. Positive. At the minus 3.4, it change the sign negative. At the point minus 1, the power of the x plus 1 is 4, so there is no change for the sign. Okay. If you want, you can check for x equals minus 2. For x equals minus 2, numerator is negative, denominator is the positive from here, so it is negative. So let's conclude to these signs. Okay, so f prime is positive in the interval minus infinity to minus 1 over minus 1 minus square root of 2. So this is increasing. Between that second interval decreasing, third interval decreasing, decreasing, increasing. For the concavity, concave down because negative, second sign of the f double prime, concave down, concave up, concave up. So as you see here, concavity change, and as you see at that point here, increasing decreasing case change, and also here increasing decreasing case change. Okay, so maybe these points can be considered as a 0. This is not correct. Okay. Also, if you want, you can show that the zeros of the function x-intercept, but there is no x-intercept. Okay. So this is our sign chart. So what is the shapes? The concave down shape this one. So in this part this is increasing, here this decreasing. So this increasing part like this one. So our graph will be like that one. Concave down but decreasing. So this is increasing part, this is decreasing part. So our graph will be like this one. So concave down again, increasing. So our graph like this, decreasing. So our graph like this one. Concave up. This is decreasing part. This is increasing part. Function is decreasing. So our graph like this one. Like this one. And concave up, decreasing part, increasing part. So it is increasing. So like this one. So now we can sketch the graph by considering the asymptotes. Actually, now you don't know the oblique asymptote, but here we have oblique asymptote. Quickly I can mention, in the future we will turn back the oblique asymptote again, okay? Actually, it should be discussed in the asymptote part, in this part. When there is no horizontal asymptote, you should discuss the oblique asymptote. The oblique asymptote for the quotient function can be calculated by using polynomial division. Actually, limit definition is the following way. When x goes to plus infinity or minus infinity, if f of x minus ax plus b goes to 0, this means y equals ax plus b is the oblique asymptote, okay? But in the previous section you learned, by using the polynomial division, you can calculate x squared plus x minus x plus 1. So minus 1. So this is minus x minus 1. So that is 2. Okay. So x minus 1 is our oblique asymptote. Okay. This is our oblique asymptote. So actually, if you check the following limit when x goes to infinity, x squared plus 1 over x plus 1 minus x minus 1. If you calculate, you will see this one, the remainder, you will find the remainder, 2 over x plus 1. So this is 0. And for x, when x goes to minus infinity, in this case, for the minus infinity case, this again goes to 0, okay? So y equals x minus 1 is the oblique asymptote, okay? So this implies y equals x minus 1 is a oblique asymptote. So on the graph, let's show that oblique asymptote. And also what we have vertical asymptote, x equals minus 1. Okay, let's show that all of our asymptotes. X equals minus 1 is the vertical asymptote. Y equals x minus 1. Y equals x minus 1. For x equals 0, y equals minus 1. For y equals 0, x equals 1. So this line is our oblique asymptote. So let's sketch the graph according to the sine table. When x goes to minus infinity, we discussed the limit here. This is minus infinity, okay? So it goes to minus infinity. When x approach minus 1 from left side, from here we calculate that limit. This is minus infinity. From right side, it is plus infinity. And when x goes to infinity, the function goes to plus infinity again. Plus infinity. So, here, by starting from the when x goes to minus infinity, f of x goes to minus infinity case. So by starting from somewhere here, because x minus infinity, y is minus infinity. By increasing and concave down shape, we will continue at the point minus 1 minus square root of 2, okay? So let's show that this point is minus 1. So this is minus 1 minus square root of 2. So increasing and concave down, but there is no x-intercept. Okay? So you cannot intersect the x-axis. So increasing concave down, it reaches that value. If you want, you can calculate this value, but it have to be negative because there is no x-intercept. After this point and until the minus 1, concave down and increasing. So the shape like this one, and by increasing it continue until the point -1. From left hand side it goes to -infinity. So behavior like this one. It goes to -infinity by approaching x equals -1 line. From right hand side of the -1, function goes to +infinity. So by starting +infinity here, and the shape is concave down and decreasing. It should be concave up. It is concave down. It is not possible. Let's check the solution. Okay, here I found the mistake. When we distribute the 2 here, this should be 2, okay? So this is 2. So this is 4. So if you cancel the x plus 1 terms, this is 4 over x plus 1 cube. So for a partition number, there is no solution. Okay, this is 4 over cube, so no solution. No solutions. We should update our sign chart. So this is not the solution, but at the point -3, okay, it changed the sign because degree is -3 now. So for f double prime, there is a mistake in the sign chart. For x equals 0, this is negative, positive, positive. So this is negative. So let's check if x is less than -1, negative. Sorry, if x is less than -1, this is negative. I am sorry. This is negative, negative, positive, positive. So at the point -1, this is correct. So this part is wrong. Decreasing concave up. So the shape like decreasing concave up shape. Concave up, decreasing like this one. Okay, now we can sketch. Here, increasing, this is correct increasing case, sorry. Again concave up. So the graph again this part is correct, that's okay, concave up. So just this part changes. So until the point -1 plus square root of 2, let's show that this point is somewhere here, -1 plus square root of 2, it is concave up decreasing graph. Graph is concave up decreasing by starting the +infinity. Okay, this is +infinity. So concave up and decreasing, there is no x-intercept, but we know the y-intercept. So what is the y-intercept? Y-intercept is, as I remember, 1. Yes. Okay, so this is the y-intercept. So by passing through this point until that point, concave up decreasing. And after this point, there is an inflection point. There is no inflection point, sorry, 1. This is local minimum. Here local maximum from the graph you can observe. Here local minimum, and there's no inflection point. Concrete change at the point -1, but -1 is not in the domain. No inflection point, okay? No inflection point. So after that point, the function starts to increase and concave up again, and when x goes to infinity, it goes to infinity. But we know that it is approached to y equals x minus 1 line, okay? So it approached y equals x minus 1 line. But also when x goes to minus infinity, it approached to y equals x minus 1 line. So y equals x minus 1 line is not correct here, or the other part is wrong. Okay? So let's sketch a bit different, because it approached to y equals x minus 1 line, and also that approach to y equals x minus 1 line. I will update this graph. since it approach y equals x minus 1 line, when x approach goes to minus infinity. Okay, here we should start the somewhere that part. We know the shape, so increasing. So this is the function where this is local maximum, and start to decrease and concave down. So our graph like this one. Okay, this is the graph of our function.